right, let's jump right in. Today, we're diving deep into one of the most fundamental pieces of Cisco ACI, the bridge domain. We're going to get past the default settings and really get a handle on the critical configuration knobs that control exactly how traffic flows through your fabric. The whole point here is to make sure you can design it perfectly for both speed and compatibility.
So here's our game plan. We'll start with the basics, what a bridge domain even is. Then we'll get into the big policy decisions, like how to handle L2 unknown unicast traffic, unicast routing, and ARP. After that, we're going to visualize how both Layer 2 and Layer 3 packets actually get from point A to point B. And we'll wrap it all up with a really practical VPC forwarding scenario.
Okay, so let's get to it. Before we start turning knobs and flipping switches, we've got to understand what we're actually working with. And at its core, the bridge domain is really the foundational Layer 2 building block inside the ACI fabric. I want you to think of a bridge domain, or BD, as a big container. It lives inside a VRF, which gives it its Layer 3 routing world. And inside the BD, you place your endpoint groups, or EPGs. But here's the most important part. The BD defines the flood boundary. It's like a fence that keeps all your broadcast, unknown unicast, and multicast traffic, your bum traffic, contained right inside that domain. Now, if you look here at the ACI interface, you can see the main policy settings that really shape the bridge domain's behavior. We're going to zero in on 4 of the most critical choices: how we handle that L2 unknown unicast traffic, whether or not we flood ARP requests, if we turn on a unicast routing to make the fabric a default gateway, and of course, how we define our subnets. All right, let's tackle our first huge decision. Picture this. A packet shows up at a leaf switch, and that leaf has absolutely no idea where the destination MAC address lives. What happens next? Well, that's what the L2 unknown unicast setting is all about. And this is a really crucial question, because the answer directly affects how efficient your network is and how well it plays with other older networks. The choice you make here is a trade-off between keeping your network quiet by minimizing floods or ensuring compatibility with everything else out there. So ACI gives us 2 main options here. The default is something called hardware proxy. In this mode, instead of just flooding the packet everywhere, the leaf sends it up to a spine switch. The spine then looks up the destination in its big mapping database, that's the COOP database, to find where it's supposed to go. The other option is, flooding, which acts just like you'd expect from a traditional network. It sends a copy of the packet to everyone in the bridge domain. And this diagram just shows that hardware proxy flew perfectly. The leaf gets the packet, says, "I don't know this MAC," and punts it up to the spine. The spine checks its COOP database. If it finds a match, like in the top part of the image, great. It sends the packet right to the correct leaf. But, and this is a big but, if that MAC isn't in the database, maybe because the host hasn't spoken in a while, the spine just drops the packet. Now let's compare that to the flooding option. When the MAC is unknown here, the leaf doesn't send it to a specific spine. Instead, it wraps the packet up with a special multicast address. We call this the Group IP Outer, or GIPO. Every single bridge domain gets its own unique GIPO, which makes sure that this flood is strictly contained only to the switches that are actually part of that specific BD. So you might be thinking, hardware proxy sounds way more efficient. Why would I ever use flooding? Well, here's why. In a super common real-world setup like this, where you're connecting your shiny new ACI fabric to an old L2 network, flooding is often a must. If there are hosts on that old network that are quiet, ACI won't know about them, and hardware proxy will just drop the traffic. Turning on flooding makes sure those packets can find their way home, and you avoid a major headache. Okay, so we've pretty much nailed down how the fabric handles unknown traffic at Layer 2. Now let's climb the stack a little and talk about Layer 3. In this next part, we're going to see how to set up the bridge domain to be a default gateway and how that choice totally changes how ARP works. The big red button for all of this is the unicast routing checkbox. It's on by default, and as soon as you give your BD a subnet address, this setting turns the fabric into a distributed Layer 3 gateway that's available everywhere for all the endpoints connected to it. It's pretty powerful. But what if the fabric isn't your gateway? What if you have a big firewall or a router that's supposed to be doing that job? In that case, and I can't stress this enough, you absolutely must uncheck that box and disable unicast routing. If you leave it on, the fabric will start learning IP addresses when it shouldn't, and you'll end up with traffic getting black-holed. Now, this flowchart shows all the logic for how ARP gets handled.
But here's the key takeaway. If you've got unicast routing turned on, but you've turned off ARP flooding to keep things efficient, ACI has a really smart trick up its sleeve. Instead of flooding the ARP request everywhere, it uses that same spine proxy mechanism we saw earlier. The request goes to the spine, and the spine forwards it as a unicast only to the leaf where the target IP address actually lives. It's a much cleaner way to get the job done.
All right, enough with the theory and the checkboxes. Let's make this real. We're going to walk through a couple of scenarios to see exactly how these settings translate into layer 2 packets actually moving across the fabric. So let's start with this simplest case imaginable. EP1 and EP2 are in the same VD, and they're both plugged in to the same switch, leaf 1. The leaf already knows that EP2's MAC address is on port E1/20. So when EP1 sends a packet, the leaf just does a simple local layer 2 switch. Easy. No fabric magic needed. Okay, now let's move them apart. EP1 is on leaf 1, but EP2 is way over on leaf 2. Leaf 1 checks its endpoint table and sees that EP2 is on leaf 2. Now, this is where the magic of the ACI fabric kicks in. Leaf 1 takes that original frame, wraps it up in a VXLAN header, and sends it across the spine. The destination of this new, bigger packet is the unique address of leaf 2, which we call its tunnel endpoint, or TEP. Leaf 2 gets the packet, unwraps it, and delivers the original frame to EP2. We've seen layer 2, so let's level up. What happens when a packet actually needs to be routed between different subnets, and we've got that unicast routing feature enabled? This is where ACI's distributed routing really shines. When a packet that needs to be routed arrives at leaf 1, it doesn't get sent to some central router. No, leaf 1 is the router. It checks its local tables, it sees that the destination IP for EP2 is located over on leaf 2, and it makes the routing decision right then and there. It then wraps up that newly routed packet and sends it directly to leaf 2's TEP. The big takeaway is that routing happens right at the edge, on the first switch that sees the packet. Okay, it's time to put all these pieces together. We're going to look at one of the most common and important designs in any data center, how traffic gets forwarded to and from a server that's connected using a VPC. The absolute #1 key to understanding VPC forwarding in ACI is this idea of a shared anycast TEP address. So leaf 1 and leaf 2 each have their own TEP address, but they also share a virtual TEP that represents the VPC pair. To the rest of the fabric, host 1 just looks like it's sitting behind this single logical TEP address. Let's trace a packet, following the red arrows, from host 2 over to our VPC-attached host 1. First, the packet hits leaf 3. Leaf 3 does a lookup and sees that host 1 is reachable through that special anycast TEP of the VPC pair. It sends the packet to the spine. Now, the spine sees 2 equal paths to that anycast TEP, one to leaf 1 and one to leaf 2. It just picks one based on a hash, in this case leaf 2, which then sends the packet down its local VPC link to host 1. And now for the return trip, following the blue arrows. Host 1 picks one of its links and sends the packet up to leaf 1. Leaf 1 does a normal lookup for host 2, finds its unique TEP address over on leaf 3, and just forwards the packet straight there through the spine. Leaf 3 gets it, sends it down the local port to host 2, and the conversation is complete. So, as you can see, the bridge domain is so much more than just a simple VLAN container. It's a really powerful policy tool. By understanding the trade-offs, the efficiency of hardware proxy versus the compatibility of flooding, and the power of distributed routing, you can finally move beyond those default settings. You can now actually engineer each bridge domain to perfectly match the needs of your applications. So the only question left is, how are you going to design your next one?